Okay, guys, um, let me open my PowerPoint here. I'm gonna okay, so we're gonna see applications of first order linear differential equations. Okay, I one examples are circuits. Okay, I just put this little circuit here. Uh, so homogeneous case. So the homogeneous case, let me show you. This is homogeneous when it's equals to 0. Okay, so that's kind of homogeneous equation. We already had defined it before, but let me say it. So what I'm gonna do in this video is give you different laws. Okay, biology laws, physical laws, and from there we are gonna deduce differential equations. Actually, this is one of my favorite topics because when we are learning calculus, we hardly see anything. If you are a mathematician, you hardly see too much of this. Okay, there is always this hurry to do equations, but we don't stop to understand the meaning. Okay, so I think physicists and engineers take a lot of advantage on that. That we as mathematicians are really proud. We just wanna talk about math, like philosophers, and don't worry to explain to other people what is good for. Okay, so this is my intention here to give over several models, and still I have much more. Okay, we're going to still do much more models in this class. So I'm just gonna read. I try to find a good book to do this. I think he does very good job. So it says that one of the earliest attempts to model human population growth. So we're gonna model population growth meaning uh, uh, you can have a lake, right? A small lake, and then you start growing fishes there. Okay, so uh, so there is a carrying capacity determined by the environment. So I already give this in my first presentation an idea of this. So it's not like or humans, we have kind of a carrying capacity. We are growing, but we are not like growing like crazy, right? So there is like some prediction, some rational way of thinking how much population we're gonna have, right? Uh, so there is a mathematician, an English mathematician, uh, Thomas Malthus in 1798, and this is called the Malthusian model. So of course I'm pronouncing this wrong. I'm not really sure how you pronounce it. I just say Malthusian model. So you guys, it's English, so you guys know better than me. Is the assumption that the rate at which the population of a country grows at a certain time is proportional to the population of the country at that time. So what is this saying? The rate at which the population grows. So first you define P of t. So what is P of t? Denote the total population of time t. So P of t is the total population of time t, and it's saying that the rate at which the population of the country grows at a certain time is proportional. So what does it mean? Rate is derivative. So we are having that the derivative of population with respect to time, the change of the population with respect to time, is proportional. This means proportional to the population at that time. So that's why they didn't put time, but it should be t. T and P of t, okay? At any time. So really what it's saying is dPdt equals K of P of t, where K is a constant of proportionality. Uh, so what is interesting here is you already have been solving this homework, right? Because it's separation of variables. So you move the 1 over p here, you move the dt here, integrate both sides and so on, and then you solve the problem, right? This model fails to take into account many factors that can influence human populations to either grow or decline. Immigration and immigration, for example. So what is it saying here? We are not considering here a lot of people coming, let's say, to United States. If we want to do that, we'll have to add plus some proportional, let's say, A of P, right? But also we are not considering people dying here. So we should have minus some constant times the population again, right? So there are other models, okay, other possibilities, okay, to add or subtract to this model. However, uh, that was the model they used from 1790 to 1860, and uh, and one is still used to model growth of small population over short time or short intervals of time. Bacterium growing, for example. Okay, so this is still a model that people use in a small time. So that's something we're gonna learn in this class, and we're learning right now. That you might have a model, and this model is just valid for small periods of time. For example, this model can be population growth for a small period of time. Now, the you guys, well, I'll talk about another model. So you have the pendulum. So that's gonna be a quiz in web work. Probably some of you already solved it. Uh, and then it has sine of the angle, right? This angle is my P, okay? And sine of angle is non-linear. It's a non-linear differential equation. It's the derivative of the angle with respect to time equals or plus sine the angle with respect to time. So it's like a pendulum, okay? So in this case, it's too difficult to solve sine of the angle. So what we do is use a linear approximation. So we just do sine of the angle equals to the angle. And then we solve it as second order differential equation. I will talk about that later. I just want to mention it here. So what does it mean? Now let's see an example. So let's say population, let's say you have 1,000, P0, let's say 1,000 bacteria, okay? After 1 hour, you have 3/2 of 1,000, so that's 1,500,000 bacteria, right? If the growth is proportional to the number of bacteria PT present at time t, determine the time necessary for the number of bacteria to triple. So you want to know how much time takes to triple the population. You have 1,000. You want to know how much time it takes to make 3,000. Okay? After 1 hour, you have 1,500. So we have two initial conditions, P of 0, 1,000, P of 1, 2,000. And we have some K, right? We don't know, but thanks to this information, we will find K. So we need to solve this equation. So here, they use another method called linear. And I'm going to make this video available. So you're going to see this video, how to solve these equations using linear method. It's also called integrating factor method. But we are going to connect it with something of second order differential equations called variational parameters. So, but you just solve it with separation variables. And they do another method. Here is you will see the video is linear equations by integrating factor, and this is the solution. Okay, so you do your separation variable, you also got this solution, and then you just plug in at t equals 0, you have 1,000, and then in the other one you just solve the two systems. You do this all the time in your pre-calculus, right? You give this problem in pre-calculus to your student. So then you'll find the time that is t equals 2.71 hours, right? So we can tell this problem is not, I mean, we kind of thinking, right? Like if in an hour I have 1,500 bacteria, maybe I'll need, in 1 hour I need 1,500, so it turns out that I need 2 hours, 2.7 hours to get it, because this is the growth. See, you graph it, that's gonna be the growth. Okay, done with example one. So another example is radioactive decay. So the nucleus of an atom consists of combination of protons and neutrons. Many of these combinations of protons and neutrons are unstable. That is, the atoms decay or transmit into atoms of another substance. Such nuclei are said to be radioactive. For example, over time, the highly reactive radium, Ra-226, transmutes into the radioactive gas radon, Rn-222. So this is the important part. To model the phenomenon of radioactive decay, it is assumed that the rate at which the nuclei of a substance decay is proportional to the amount, more precisely the number of nuclei, AT, of the substance remaining at time t. Okay, so again we have the rate of change is proportional to the amount at any time. So we have the same kind of equation. You see, equation 1 and 2 are exactly the same. The difference is that in one case you have population growth, in the other one you have population decay. So this is good because, here the derivative is going to be negative. In the other, the derivative is positive. In countries that don't grow too fast, like I guess Denmark and all those countries, this rate is really small. Okay. And then here is this is going to be connected to the next problem. Another way to do this is, in physics, the half-life is a measure of the stability of a radioactive substance. The half-life is simply the time it takes for one half of the atoms in an initial amount A sub 0 to disintegrate or transmute into the atoms of another element. The longer the half-life of a substance, the more stable it is. For example, the half-life of highly radioactive radium is about 1,700 years. In 1,700 years, one half of a given quantity of Ra-226, of radium-226, or radioactive radium better, is transmitted into the radon. The most commonly occurring uranium isotope, I don't remember how to pronounce it. So it has a half-life of approximately 4.5 billion of years. Okay, 4.5 billion of years. One half of a quantity is transmuted into lead. Okay, so this is pretty sad, right? Because we know that with uranium, they do really bad stuff, right? So do you know how much time it's gonna take to disappear? Okay. Anyway, so a breeder reactor converts relatively stable uranium into the isotope plutonium-239. After 15 years, it is determined that 0.0443% of the initial amount A0 plutonium has disintegrated. Find the half-life of this isotope if the rate of disintegration is proportional to the amount remaining. So I learned this when I was learning English. I figured out that if it's in Spanish, you'll say isotopo. So in English, usually the pronunciation should be even, the accent should be even before. So maybe it should be isotope. I don't know. You guys tell me if I did it right. If my law of pronunciation of Spanish version to English applies. So we'll see. So let AT denote the amount of plutonium remaining at time t. As in example 1, the solution of the initial value problem is this, right? So this is my equation. This is a linear homogeneous differential equation. First order. So many adjectives, right? First order because I have only one derivative. Linear because I don't have squares or sines or cosines of A or anything like that. Okay? It's called initial value problem because you have an initial condition. So then you know the solution already. Okay, I bet you guys teach this in your pre-calculus. You give the kids this solution, and they need to find A0 and K, right? So you just proceed as pre-calculus, and you will find your T. Okay. Next one, Newton's law of cooling. Another really cool one. Okay. According to Newton's empirical law of cooling, and again, all these laws, you know, I don't expect you to, oh, what I didn't think about this before. I should know this. Well, those are laws that they are sectoral laws because everybody in any lab has been experiment checking this and they get the same constants. Okay, so they verify it. So this it's just for us. It's just a law. We use math and then apply it. Okay. Um, so the rate. So what this law says, the rate at which the temperature of a body changes is proportional to the difference between the temperature of the body and the temperature of the surrounding medium, the so-called ambient temperature. So for example, I don't know if you guys watch Wheel of Fortune. They never have these questions there, right? But they talk about cooking and all. So let's put this in terms of cooking. Let's say you have a cake, right? So you got your cake, you're cooking your cake, and you wanted to cool it down, right? So people is coming to your apartment to your cake. So how much time you need? So you get the cake out of the oven and be waiting for people so they can eat the cake. Because what about you make the cake and everybody drink their wine, whatever, and then they're ready to go, and still the cake is not cooled down enough to be eaten, right? So yeah, so it's very practical problem, very useful. So T of T represents of the temperature of the body at time T. It means how the temperature of your cake. Tm the temperature of the surrounding medium. So let's say you are 75 degrees in your or 70 degrees. I like 70 degrees. 70 degrees in your apartment. So you take the cake and put it to cool down. The surrounding median is 75 degrees. So one question could be, how much time takes for my cake to cool down? To cool down at 70 degrees, okay? And the room temperature. Well, 70 degrees probably is too cold, huh? Maybe you wanted 85 or 90, I don't know. So this is really great again because the rate of change is temperature, change of time, is proportional to the temperature of the cake minus the temperature of the surrounding. So this is proportional. Okay, so it will be great, and if we Wheel of Fortune, we have these kind of questions. You know, this instead of Wheel of Fortune in France, they have this very popular like 3:30 or 4 p.m. I remember, it was in the middle of the day, but they were really good questions, really good, really interesting. I mean, like, it's really easy to get used to sit down and pay attention, and we should improve the Wheel of Fortune a little bit. Okay, so we have so when a cake is removed from an oven, its temperature is measured as 300 Fahrenheit degrees. 3 minutes later, its temperature is 200 degrees Fahrenheit. How long will it take for the cake to cool off to a room of temperature of 70 degrees? So this is your equation. dt equals a constant that you don't know, T minus 70, and the initial temperature is T0 equals 300. 70 because that's the surrounding temperature. So you just do, here you are doing, I like it, separation variables. You see, separation variables. Yeah, that's your T of T. And then what it says is how long it will take for the cake to cool off, right? So what is interesting here is that the solution is 70 plus 230 E times something. You see, this temperature, it says, is always gonna be hotter than 70 because this guy is never negative, not even zero. So that's what they take the limit. The limit means that the coolest this cake can get is 70 degrees. It cannot get cooler than that. Is that cool or what? Yeah, it's really cool because your cake is never gonna be cooler than the surrounding temperature, following our mathematical model. And I found that kind of interesting. However, sometimes mathematics has their limits. So, but so if one day you're eating your cake and your cake is cooler than the temperature environment, or if it's kind of getting frozen or something weird is happening in your apartment. Maybe it's the air conditioner is not 70 degrees, it's lower. I don't know. I'm in a good mood. Sorry, guys. Many jokes. It's probably because I like this topic. I was waiting for this to get you to some interesting interpretation of this equation, right? So hopefully you share it with your students too. And now and further go and read this book and explore more books. I think we need to start doing more explaining things in in a different way to get students encouraged. I mean, you see those kids on tablets, on cell phones. If we start using applications, I don't know. So we can feel free to talk about these kind of issues in your videos. I think it's interesting for all of us. How can we, as teachers, can we improve everybody else learning process and ourselves, right? So for a series circuit containing only a resistor and inductor. So this is now a circuit. Okay. So this is usually a battery. Okay. So you put a battery and you want to know how this is gonna move around, or the energy is gonna move around here, right? For a series circuit containing only a resistor and an inductor, Kirchhoff's second law states that the sum of the voltage drop across the inductor and the voltage drop across the resistor is the same as the impressed voltage E of t. So that's what I'm saying here, that the impressed voltage is E of t. So be aware, this is my first non-homogeneous differential equation because I have an external battery producing energy. Okay. So we said that the inductor, the voltage drop across the inductor, right? And that's L di dt, and the voltage drop across the resistors, I times R, okay, is the same as the impressed voltage. Okay. So that's very interesting. So the amount impressed over here is the same that L times di dt, the length of this guy, plus R, that is the length. Well, not the length. Well, I'm gonna here where L and R are constants known and the inductance and the resistance, respectively. Okay, so this is L and R are constants determined for us, inductance and resistance. Basically, the circuit is gonna tell you how much is L and how much is R, and then you figure out your equation, and from the battery how much voltage you have. Okay. The current. So what is IT? The IT is the current. I should put this in yellow. It's also called the response of the system. Now, on the other hand, we have another circuit. This is called RC series circuit. This was called LR series circuit. The RC series circuit, the voltage drop across a capacitor with capacitance C is given by QT divided by C, where Q is the charge on the capacitor. Hence, for the series circuit shown in this figure, Kirchhoff's second law gives the Ri plus 1 over CQ equals ET. But turns out that the current I and charge Q are related by this formula. So the derivative of charge is current. And then we have a linear differential equation, non-homogeneous. So we have two linear homogeneous equations, non-homogeneous equations, sorry, and then you will have those in your home. So an example, you place a 12-volt battery. It's connected to a series circuit in which the inductance is 1/2 Henry and the resistance is 10 ohms. Determine the current I if the initial current is 0. So I did put here my, this is an LRC series circuit, so it has all these guys, okay? But then you'll have, if you put the three of them, you will have a second order differential equation with external. That's not a homogeneous second order differential equation. Guess what? We haven't not solved that. That's what is next. But here I did put my L is inductance, Henrys, resistance in ohms, and capacitance in farads. Okay. So, farads. So I have here 1/2 di dt 10I equals 12. So here you have to use the new video on separation. Oh, no, separation. No, on linear equations. Okay, and that's why you will solve it. Okay, and then there you go. There is your current. Okay, so let me see. So what is next is what I said, a whole LRC circuit, series circuit, and then we'll have a second order differential equation, non-homogeneous. That's what is next. Okay guys, thank you for watching. I wish I could put you can give me a like or not. Okay, bye.